This is Scott Palmer representing Group 6.
In this presentation, we will go over Chapter 10. This chapter is learning that if testing is only performed a few times a year, developers learn about their mistakes months after they introduce the change that caused the error. By then, the link between cause and effect has likely faded. Solving the problem requires firefighting and archaeology. And worst of all, our ability to learn from the mistake and integrate it into our future work is significantly diminished. So it's important to perform automated testing because without the more code we write, the more time and money is required to test our code, and we can provide real value to the customer. Case point Google. Google exemplified a culture that values automated testing scale. In 2005, there was a problem with Google Web Server team when the teams couldn't make changes to the server, which caused other issues that affected the testing for reliability and testing time prolongation. Mike Blaine describes how it affected developers deploying changes. He describes fear as mind controller. It controlled experienced people as well as unexperienced people to make any change to the system. As Mike Blaine describes, they claim no changes are to be made to Google Web Server without accompanying automated tests. They adopt alternative ways to pass their testing regulations. Perform continuous build, tests, and integration practices and environments help to achieve the purpose is this chapter. It's key to have developers build automated tests as part of their daily work because it creates a fast feedback loop that helps developers find problems early and fix them quickly when there are the fewest constraints. Here, automated test suites are created. They increase the frequency of integration and testing of the code and the environments from periodic to continuous. According to the image, it is done by building the deployment pipeline, which will perform integration of the code and environments and trigger a series of tests every time a new change is put into version control. It's important to know that the development pipeline ensures that all code checked into version control is automatically built and tested into production-like environment. It helps to find any errors promptly. We must create automated build and test processes to achieve that. This is critical for the following reasons. The process could run all the time. A segregated build and test process ensure that we understand all dependencies required to build a package and run the test code. Next, we can package our application to enable repeatable installation of code and configurations into an environment. Instead of putting our code into packages, we may choose to package our applications into deployable containers. Next and last, environments can be made more production-like in a way that is consistent and repeatable. Explaining the deployment pipeline, running the commit stage, which builds and packages the software, runs automated unit tests, and performs additional validation such as static code analysis, duplication, and test converge analysis, and checking style, then acceptance stage automatically deploys the packages created in the commitment stage into a production-like environment and runs the automated acceptance tests. Through each stage, the code could be deployed into production, providing everyone in the value stream, especially developers, the fastest possible feedback. Also, the deployment pipeline becomes a key in the developmental process. This happens through the history of code building. Detailed information regarding which tests were performed and which tests matched which environment is presented. Now that we have a working deployment pipeline infrastructure, we must create our continuous integration practices, which require 3 capabilities. A comprehensive and reliable set of automated tests that validate we are in a deployable state. Next, a culture that stops the entire production when our validation tests fail. And last and third, developers working in small batches on trunk rather than long-lived feature branches. In a project, there are various stakeholders that are involved, like the developers. They introduce changes into the code or change configuration settings. It could possibly break the automated tests and builds. If the feedback is slow and periodic, the troubleshooting would not be effective, and the difficulty of successfully diagnosing and fixing the problem would be null. To prevent that, we need fast automated tests that run within our build and test environments whenever new change is introduced into version control. In this way, we can find and fix problems immediately. Automated tests fall into one of the following categories. Unit tests. These typically test a single method, class, or function in isolation. For many reasons, including the need to keep our tests fast and stateless, unit tests often stub out databases and other external dependencies. Acceptance tests, which humble and fairly define the difference between unit and acceptance testing as, quote, the aim of a unit test it is to show that a single part of the application does what the programmer intends it to. The objective of acceptance tests is to prove that our application does what the customer meant it to, not that it works the way its programmers think it should, end quote. Next, integration tests. Integration tests are where we ensure that our applications correctly interact with other production applications and services, as opposed to calling stubbed out interfaces. Integration tests are performed on builds that have passed our unit and acceptance tests. Because integration tests are often brittle, we want to maximize the number of integration tests and find as many of our defects as possible during unit and acceptance testing. To find errors early in testing as possible, it is necessary to run faster running automated tests, example unit tests, before slower running automated tests, example acceptance and integration tests, which are both run before any manual testing. The priority is that any errors should be found with the fastest category of testing possible, but if our errors are found in our acceptance and integration tests, the feedback we provide to developers is orders of magnitude slower than with unit tests. Therefore, we find an error with an acceptance or integration test, we should create a unit test that could find the error faster, earlier, and cheaper. Martin Fowler described the notation of the ideal testing pyramid, where we are able to catch most of our errors using our units test according to the image. If we find that unit or acceptance tests are too difficult and expensive to write and maintain, it's likely that we have an architecture that is too tightly coupled, where strong separation between our module boundaries no longer exists, or maybe never existed. In this case, we will need to create a more loosely compounded system. To achieve the purpose to have fast the tests, we need to design our tests to run in parallel, potentially across many different servers. We may also want to run different categories of tests in parallel. For example, when a build passes our acceptance test, we may run on our performance testing in parallel without our security testing, as shown in Figure 15 provided. We may or may not allow manual exploratory testing until the build has passed all of our automated tests, which enables faster feedback, but may also allow manual testing on builds that will eventually fail. Any tester, which includes all developers, should use the latest build that has passed all the automated tests, as opposed to waiting for developers to flag specific build as ready to test. By doing this, we ensure that testing happens as early in the process as possible. One of the most effective ways to ensure we have reliable automated testing is to write those tests as part of our daily work using techniques such as test-driven development, known as TDD, and acceptance test-driven development, known as ATDD. This is when we begin every change to the system.
by first writing an automated test that validates the expected behavior fails, and then we write the code to make the tests pass. This technique was developed by Kent Beck in the late 1990s as part of extreme programming and has the following 3 steps involved. 1. Ensure the tests fail. Write a test for the next bit of functionality you want to add. Next, ensure the tests pass. Write the functional code until the test passes. Last, quote, refactor both new and old code to make it well constructed. Ensures the tests pass. These automated test suites are checked into version control alongside our code, which provides a living, up-to-date specification of the system. Through manual tests, the developers can work on high-value activities that cannot be automated, such as exploratory testing or improving the test process itself. However, merely automating all the manual tests may create undesired outcomes and could generate false positives. A small number of reliable automated tests are always preferable over a large number of manual or unreliable automated tests. Now, wrapping up this topic, we could start with a small number of reliable automated tests and add them over time, creating an ever-increasing level of insurance that will quickly detect any changes to the system that takes us out of a deployable state.